have maybe because the denominator is a sum of two functions. So first, we were asked, by the way, we were asked to determine h prime of 4. Okay, so first I have to find h prime of x. I have to use the quotient rule, function prime. So remember, this is the way I like to use it, but you can, you know, create your own style. I'm fine with that. But for me, it's easier to say 1, 2, 1, 2. But for you, it may be something else may be easier. If, you know, if it works for you, it works for me. Okay, so g prime times the second function minus g times the bottom function prime. So this is f prime of x plus g prime of x over f of x plus g of x, everything squared. Now, all I have to do is just copy those numbers. So back to the problem, I'm given that f of 4 is 2. So this will be 2, and this will be 2. Then I'm given g of 4 is 5. So this is 5, this is 5, and this is 5. And f prime of 4 is 6. So this is 6. G prime of 4 is negative 3. So this is negative 3, and this is negative 3. So now from here, you just have arithmetic. So negative 3 times 7, and this is 3 times 5 with minus in front, and this is 7 squared, and you will get your number. Is that okay?
Yes.
Can I stop here, or you want me to continue with those numbers?
No, you can stop there.
Okay. Other questions? My pleasure. Other questions, anyone? Did you come across anything that you would like to discuss in 3.1 or 3.2?
Number 7 in 3.2.
Number 7 in 3.2. Where is this from?
The web assigned.
The web assign. Number 7. I did write a note for you about the test. Overall, I'm super pleased. Thank you very much. Everyone can still get an A in the class, but you really have to try to catch up, a couple of you. I'll do anything to help you. Just you have to do the work, please. And stay with me, because falling behind is disastrous in this class. Okay, 7 in 3.2. Let's see what 7 is all about. 7, 5, 6, 7, 7, 7. Okay, so let's take a look. So this is a typical situation in which I highly recommend simplify before you try to differentiate. So what I would recommend here is multiply. So copy the base at the exponents. So we have 5 halves, and then plus c, v to 3 halves, e to v. So now when I differentiate, this is easy because it's 5 halves v to 3 halves, 5 halves minus 1, which is 3 halves. I recommend leave c outside. Deal with the rest because c is a constant. You don't have to worry about it. So 3 halves, v to 3 halves minus 1, which is 1 half, e to v, plus v to 3 halves, e to v prime, which is e to v. So remember, I use the product rule the way I like to use it. It's up to you. I accept any method as long as it's correct. It's definitely acceptable. So you don't have to do anything, just distribute c. C is a constant. So 5 halves v to 3 halves plus 3c over 2, v to 1 half, e to v, plus c, v to 3 halves, e to v. And that's it. Any questions? I know maybe it was a little bit fast, but let's take a moment and ask any questions, please.
Can we leave the answer like that, or do
Oh,
we have
yeah,
to factor
of
out
course,
each
yes, absolutely, please, yes. 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 Absolutely. There is no need to do anything else here. Anything else? Anyone? Okay, so in that case, I would like to start 3.3. And I just realized that I did not put my upload there. I was just thinking, did I do it? Did I do it? No, I didn't do it. No, it is. Okay. Good. So our next step is derivatives of trig functions. So number 2, that's section 3.3, derivatives of trig functions. So we're looking at sine, cosine, tangent, cotangent, secant, cosecant. And we can prove any of these if you'd like. It's a long proof, doable with identities, trig identities, etc., etc. But I would like to move ahead, and if you decide to, just let me know. Negative sine x, tangent prime is secant squared, cotangent prime is negative cosecant squared. Secant prime, remember, is secant tangent, and cosecant prime is negative cosecant cotangent. So these are the 6 trig functions and their derivatives. There is a function that is very important, and that function is sine x over x, or sine theta. Let's spice it up a tiny bit. So this function is an important function because of different situations, but mainly because of this limit. So whenever we want to look at the limit as theta or x approaches 0 from sine theta over theta, can anyone tell us what is the initial assessment for this? How much is sine 0 over this?
That'd be 0.
Very good. Over 0. But now we know something very important, that every time we have a fraction of whatever, and the initial assessment is 0 over 0, and it has a limit, so these conditions are absolutely mandatory: a limit, ratio, initial assessment 0 over 0, or infinity over infinity. What method can we use, or theorem, basically?
L'Hopital's.
Very good. So then we have limit as theta approaches 0. Can anyone give us a derivative of sine?
Cosine.
Theta, very good. And the derivative of theta?
1.
Very good. So please plug it in and tell me the answer. If it's still 0 over 0, we can continue. Differentiating again. I have to reach Plug my computer in. It's running
One
on.
over one.
Very good. So the answer is, that's it. Great job. However, this is so important that we have to look at it in the following way. Limit as long as these pieces are all the same, the answer will always be 1. But everything has to be identical. This has to approach 0. These two, all these three have to be the same, and only then the answer is 1. Now, what happens if I have a 2 in here, for example, or a 3 in here, for example? What will the limit be?
Two over three.
That's it. Of course, it will be 2/3. Of course. Thank you. Okay, so let's see how this concept is applied. And I would like us to look at a few limits so we can see how this works. And here they are. I would like to start with something simple. I can't find anything simple really in this book. So I'm just going to start with this. Limit Sx approaches 0 from sine 4x divided by sine 6x. And you could say, wait a minute, I don't see any connection. What's the connection between this and this? Okay. Before I continue, I also would like to explain that this is true even if they're flipped. So it's the same answer even if I have theta over sine theta. Not sine theta over theta, but also theta over sine theta. So I'm going to write it here on the side. So the same thing with limit as theta approaches 0. From theta over sine theta, the answer is still 1. Because you get 1 over cosine instead of cosine over 1, and the answer is still 1. Same thing. So I know, and you're going to say the same thing, and I learned this from my students. I never really thought about it till one of you guys or your peer students a long time ago said to me, see, your calculus is 1 line and your algebra is 5 lines. I agree. So looking at this is what I see. Limit as x approaches 0. I didn't do anything. I just prepared the function for what I need to use. Right? So, but this is the same thing because sine times 1 is still this and 1 times sine is still this. But I realized immediately looking at this function of a ratio of 2 sines that I can get to 0 over 0 out of it as long as I replace this by 4x. In other words, I'm multiplying it by 4x, but if I multiply the denominator by 4x, I have to multiply the numerator by 4x. I cannot just decide, oh, let me change 1 into 4x. No, 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 no. If I multiply 1 by 4x, I have to do the same thing. And of course, what I need here is to change or have this 6x, but if I multiply the top of this fraction by 6x, in order not to change the value of the function, I have to do the same thing in the denominator. And then you can say, but wait a minute, because your box is not the same. It's not. However, When x approaches 0, 4x approaches 0. When x approaches 0, 6x approaches 0. So, although, and I can replace this by this, it's the same thing. If I say to you that x approaches 0, I really tell you that 4x approaches 0 or 6x approaches 0. So by manipulating the function, I realize that this piece will go to, and you'll tell me, and this piece will go to, and you'll tell me. Where is, when 4x approaches 0, where is sine 4x over 4x going to?
Zero.
Careful, let's take a look. As long as the box here, and the box here, and the box here are all the same, the answer will always be 1.
Oh, so 1.
1, indeed. So this is 1, and this is 1. And now, what is the limit? I still have a 4x and a 6x, but the x with the x will simplify. So I'll simplify x, and what is the final answer? I don't need to copy the limit operator again, because I now have just the final answer, which is?
4 over 6?
Yes, awesome. Indeed. Perfect. So without, say it again.
I said sorry, I forgot to simplify.
No worries. 4, 6, fine for now, and then 2/3. Let's write it here just to make sure everyone sees that. So without this concept, okay, I had other options because we already talked about L'Hopital's rule. We could have used L'Hopital's rule, but we don't know how to differentiate a function of a function yet. It's the next step. So we couldn't really, at this point, use L'Hopital's rule. But it is 0 over 0, so L'Hopital's rule is applicable. So here was the alternative. To make sure that these three are the same, and the answer will be 1. Okay, so let's look at another example.
Wait,
Yes, any question?
4x equal 1 and not 0?
Say that again.
Why does 4x equal 1 and not 0?
But I'm not looking at the limit from 4x. I'm looking at the limit from 4x over 6x.
Mm-hmm. But when you plug in the limit operator of 0...
But you have to simplify. You have to simplify first. I simplified by x first.
Oh, yeah, I see now. Thank you.
Sure. So we have to simplify by x first, and then 4, 6 changes into 2/3. Is that okay? Everyone?
I'm not sure I quite